Okay, hello everyone. Hello and welcome to the lecture on MRI the Basics Chapter 19 entitled Fast Spin Echo. So the goals from this chapter are to be able to describe this fast spin echo, or also called a turbo spin echo pulse sequence, and also the type of image contrast it provides, and then some of the trade-offs that are going to be involved with what do we get when we go to this sequence that is very fast and very efficient. What is the downside? Okay, so what a fast spin echo or a pulse sequence is basically a sequence of multiple spin echoes, as illustrated here and as we have already covered a little bit and alluded to in the previous chapters on spin echo imaging. Okay, and it's basically a 90-degree excitation followed by multiple 180-degree pulses in which we're continually refocusing the transverse magnetization to continue to get this refocusing of the T2 star phenomena, so we only have T2 decay. And we can basically repeat this until the signal is almost gone. There's a few other names for this technique, sometimes called, so fast spin echo is the name that GE at least uses. Turbo spin echo, or TSE, is used by Siemens MRI systems. Another name is rapid acquisition relaxation enhancement, or RARE imaging. And these are extremely popular because they're a very efficient imaging technique. They have a lot of signal to noise, provide very rapid imaging. And the sort of main kind of gotcha or unique parts about these sequences is that K-space is covered at these different echo times. And so this will both affect the image quality, but also determine the image contrast, as we'll cover. Okay, so we have a couple of new terms we're going to define for our fast spin echo sequences. The first of these is the echo train length. So in this example, this is the number of spin echoes that are created. So in this sequence over here, we would have an echo train length, or ETL, equal to 4, because we have 1, 2, 3, 4 spin echoes created. Okay, the next term that we're going to define for these sequences is what's called the echo spacing, or use this notation TESP. And this is the time between the individual spin echoes. And for these types of sequences, these are symmetric in time, so there's always a consistent spacing between the echoes. So we have this consistent echo spacing. And then the final thing is, what you'll notice with this sequence, right, is that we actually, in fact, have multiple different echo times, at least by the definitions that we've used before. We have a first echo time for this first spin echo, and I'll often use this notation, TE1, TE2, TE3, and we can squeeze it in, TE4 here as well. So when we're trying to determine contrast, or we want to pick an echo time that characterizes the sequence, what is that going to be? And that's going to be what I like to call the effective echo time, or TE effective. And this is going to depend on the K-space trajectory that's traversed. Okay, to illustrate how we determine the echo time or the contrast in fast spin echo, we need to draw the pulse sequence and illustrate how we acquire our phase encodings and how we traverse K-space during a fast spin echo sequence. So here we start off with 90-degree excitation into the transverse plane, and then we're flipping over and then allowing for refocusing of the transverse magnetization at these regular intervals at this echo spacing. And then I'm going to add in our frequency encoding gradient here, which, because the 180-degree pulses have the effect of inverting the phase or flipping us around in K-space, the gradient pattern like this is going to have us continually going across, flip back over the 180, across, flip back over by the 180, and so on for the K-space trajectory here. So the frequency encoding is sort of not providing any difference between the different echo times here, but it is the phase encoding that allows us to move for the different echo times at different locations in K-space, and this is what's going to determine the image contrast. So I'm going to draw some example of what we might do, and as I'm drawing this, you can think of, okay, what is the K-space trajectory here? And then we can illustrate it. So in the first interval here, we're going to start at the center of K-space. We're going to go out to some positive Kx. 180-degree pulse is going to flip this around. Then this little gradient here is going to bring us down to our phase encoding line. We're going to acquire that line, move back up with this subsequent gradient. Then the 180-degree pulse is going to flip us around, and on the next TR, we're going to go down to a different phase encoding line here. And so on. In this interval, we're going to acquire our center phase encoding line, and here I'm putting things in a sequential fashion, but we don't need to do this, as illustrated in some of the subsequent slides. Next TR is going to be moving up to a higher line in K-space. And so on. Better add the data acquisition windows here. Okay, so this is really the core of what we'll be able to do with a fast spin echo, is we can acquire multiple phase encodings within our TR. So we can do a line at each spin echo. And it turns out that our echo time or effective echo time is going to correspond to when we go the closest to the center of K-space. And sometimes I'll use this notation again, TEF effective. In this case, it's the green data acquisition window here, where we're going right through the center of K-space. And the reasoning for this is that most of our information, as you've seen in K-space images, there's most of the information, most of the amplitude in K-space is near the center. So whatever weighting we put on the signal at the center of K-space is what defines the majority of the contrast. Again, because what we're putting on the spatial information there is getting weighted by, say, the T2 decay in this case, and most of the spatial information is weighted by the T2 decay from the phase encodings where we're crossing the center of K-space. Okay, so this last line here is what's going to be our rule of thumb for how we're going to determine the fast spin echo time. And I'm going to write this in this notation, and so let me introduce this here. Where let's redraw this K-space sampling pattern, where here our first spin echo, we're simply ordering our first spin echo to our last spin echo as we moved across K-space. And now what we want to think about is, well, each of these echo times has a different TE over T2 weighting. So this is going to be described by this WKY weighting function here, where at this point here, it would be whatever the T2 weighting is at the first echo time, then the spatial information in K-space is going to be weighted by now some increased decay at the second echo time, and so on. So this weighting function is getting applied on top of the spatial information, on top of the K-space data that tells us the shape, the edges of our object. And so this is going to have, and so it might have, well, I didn't quite draw it exponential, but it's going to have some more or less exponential shape. So the K-space data that we get are capital M hat of, in this case for 2D, kx, ky is going to equal our spatial frequency information, or our ideal K-space data, just capital M, but multiplied by this weighting function in ky. Okay, so again, what this is saying is that we have our ideal data, capital M. What's happening in the fast spin echo is we have some additional weighting factor here that's due to the T2 decay across the echo times. So now say we wanted to look at what the effect of this was on the image, we would use our Fourier analysis. Say, okay, what's our image, lowercase m hat? And we're just going to get a little bit further here, and then I'm going to sort of give you an intuition, but it's going to be the multiplication. It's going to give us our ideal or sort of perfect image, but convolved with the Fourier transform of this weighting function. And I put this in a very general sense here. So this applies for this like exponential weighting, but there's other phenomena we could apply this to as well. And this this weighting function here is going to capture two things. Okay, it is actually going to capture our TE contrast, but a convolution also typically leads to some sort of blurring or spreading out of the signal, and in the case of for like this kind of decay across k-space, we will in fact get some sort of blurring of our image in the y direction. Okay, so this weighting, this change is happening in the y direction, just like when we covered motion artifacts. And motion artifacts were due to changes in signal amplitude in the y direction, leading to the artifacts in that direction. Same idea here. The signal fluctuations due to T2 decay across echo times are happening across the ky dimension, so they're going to lead to this blurring in y. And ultimately, this is going to put a limit on how many of the lines or how long our echo train length can be. And this is in fact one of the trade-offs of the fast spin echoes, is that we don't have now quite this as clean of a representation of our k-space data. But it turns out for a lot of cases it's pretty darn good, and this blurring is pretty tolerable. Okay, so now we can the concept of the effective echo time, saying, okay, well, let's cover the center of k-space at the echo time that we want to be weighting our data by for our T2 weighting. So we can do something like, so previously we started with TE1 at the bottom here, but we can actually start with TE1 right at the center of k-space here, and then do something like this. So let's change this to where we would acquire our later echo times data as we go further out. Oops, further out in k-space. And so this would give us, so we go back to the pulse sequence diagram and just redesign those phase encoding gradients for the given spin echoes, such that we go to the center of k-space first, and then we get this weighting function where we have the highest amplitude weighting at the center, and then this decay is kind of happening as we go away from the center of k-space, and this will also lead to, again, some sort of blurring. Hey, but this would basically give us a short effective echo time. So actually with this we can do our short TE contrast, like T1 weighting and proton density weighting with the fast spin echo sequence. But also a very common use case is to choose to cover the center of k-space at one of the longer spin echoes. And I'll just draw this in the extreme case, where we could start on both edges of k-space and then gradually move towards the center. And with our last spin echo or our last echo time, we'll cover the center. So we'll get sort of the lowest signal weighting. When we cover the center of k-space. And so this, of course, would be good for T2 weighted imaging. And all we would do in the pulse sequence to make these manipulations is modify those phase encoding gradients such that we choose at which of the spin echoes we cover the center of k-space. So which of the spin echoes we weight the most information-rich spatial frequency data. Another sort of way you can extend the fast spin echo is, in fact, we can do 3D pulse sequences with the spin echo. So similarly to how we did a 3D gradient echo, you can do a 3D fast spin echo, and this is a technique that's a little more recently come into clinical use. So we can do our same frequency encoding gradient as the previous example, but now we'll need to do frequency phase encoding in 2 dimensions. And so I'll map out where the k-space locations would be for the gradients as I've drawn them. So let's start back at the end here, where we're going to be doing positive GZ and positive GY. So in this KYKZ plane down here at the bottom, we're going to be covering this quadrant. The 2D view would be going across in the X direction. Let's go back to the beginning here. Initially, keep in mind we'll be at the center here. Let's in this first interval here, let's call this purple, we're going to travel to positive location in KX. The 180-degree pulse flips us around. We're going to go negative in KY and KZ. Due to these negative phase encoding blips, we're going to do our frequency encoding readout, move back to the center, and then repeat. We're going to go out to this corner here, the next TR, or the next, sorry, not next TR, the next spin echo. Just the KY plane, we can't, oops, no, I guess I have drawn that a little backwards here, let's see. Sorry, that was negative KY, so still, I guess this plane is correct. Okay, positive KY, negative KZ, brings us up to this location, positive KY up here. And so we're covering now, what we're illustrating here is we're covering this 3D k-space, okay, with 2 dimensions of phase encoding indicated by the X's in the bottom right here, and then frequency encoding in the 3rd dimension here. So these techniques in rare, FSA, TSC have some massive advantages. They can be extremely fast and have very high SNR because of this continued refocusing of the transverse magnetization. It's really taking advantage of all the transverse magnetization very efficiently. Okay. And so for these two reasons, they've just become incredibly popular and incredibly powerful pulse sequences. And again, it's rare to do, no pun intended, to do like a single spin echo sequence. I mean, with the exception of probably diffusion weighted imaging, but any T2 weighted imaging is probably almost all is being done with a fast spin echo or a turbo spin echo sequence now. The cons to be aware of is there is a little bit of sort of a mixed contrast and T2 blurring, and that's what we're describing with this weighting function across the phase encoding lines, because you inherently have T2 decay across the different phase encodings that you're acquiring for the multiple spin echoes. And again, this turns out this is not a deal breaker for most applications, very tolerable, but there is sort of an upper limit on how many echoes or the echo train length that can be used. The other thing is there's a lot of RF power. 180-degree pulse is the biggest flip angle that we use, and it's being used a lot in a short period of time. So these sequences tend to be, especially like 3 Tesla, can be near the FDA limits for the specific absorption rate, or SAR, that limit the amount of RF energy you can deposit into a subject so there's not too much heating. And I'll say from personal experience, I've been in testing of these sequences, and you can get a little bit warm when they're running some of these. There's a couple advanced implementations of this. We talked briefly about 3D fast spin echo, which now is something you should be able to understand both from your knowledge of spin echoes and K-space and 3D imaging. There's something a little bit more advanced called using variable refocusing flip angles, which is a trick that does help to reduce the SAR and also extend the echo trains. And this uses an interesting technique called extended phase graphs as a way to understand that. And then some other tricks you can play with the multiple contrast as well. Okay, and with that concludes this lecture on fast spin echo pulse sequences. Then now you should be able to describe these pulse sequences both in terms of the RF as well as the imaging gradients, and how this relates to the image contrast and some of the advantages as well as the trade-offs of the techniques. All right, thank you for watching.